So I'm not going to teach integration how it's usually taught, through some sort of example using velocity of a car, or how I might be able to get the displacement using the velocity of a car. However, I'd like to show you a method just by using mathematics. This also gives us a much better way of understanding how integrals relate to derivatives, and thus will help you solve problems later on when you have to apply the relationships between integrals and derivatives. So, what if I took a function like this and asked you what the average value of the function is between these 2 points, the origin and a? How would you go about answering that? Now, taking the average of a finite value is pretty simple. If I have terms like 5, 6, 10, 9, 4, I can just add them all up. So 5 plus 6 plus 10 plus 9 plus 4, and divide them all by 5 itself, by the number of terms, right? And this is what the average is. It's the sum of all the values divided by the number of values you have, and that is pretty easy to take when you have a discrete number of variables, or a discrete variables. Let's say we're given a discrete function that looks something like this, and we're given their values. And right now we'd assume that they're all of equal width. So all this could be 1, 2, 3, and 4. So again, that's very simple. If we wanted to find the average height of this function, we would add 5, 6, 4, 3 and divide them by the number of terms that we have, which is 4. Uh, but now let's say that they all aren't of the same width. Let's say this is 1, this is 3, this is 5, and this is 6. So now this has a width of 1, this has a width of 2, and and a width of 1. So what we would do is we would take 5 times 1 plus 6 times 2, because that has a width of 2, plus 4 times 2 plus 3 times 1, and then divide all of this by the total length, which is 6 units long, right? So that's just something like a weighted average that we would be taking of things that aren't really as uniform. And we would just need to keep these two things in mind while approaching how we would take the average height of a function. So the average height of a function is the same as asking what's the average value of the function, as we're assuming f of x is equal to y. And taking the average of an infinite number of points would give us something like a huge sum of all these lengths. So let's say I had all these lengths, like an infinite number of lengths. So we'd have the sum of all these lengths, something like that, and going on forever, and then divided by infinity, which doesn't really make sense. Let's call this AVG of the function. It doesn't really make any sense, and we can't really divide by an infinite value. So the best way, and a good way to approach a problem, a good way to approach a problem where you want to use infinity, but when you do use infinity, it doesn't really make any sense, is using limits. And we've covered limits before, and it is a good way to use infinities without technically using them. So, if we wanted to approximate that same average value of the function, I'm just going to draw it again. So let's say it's from here to here, and it's any function f of x equal to y. And I wanted the average value, let's say, as when this is a, between 0 and a. How would I go about this? So let's take an approximate value, and similar to the previous discrete function that I had shown you, if we take values, these values at certain intervals, let's call those intervals, let's call the width of those intervals n. Okay, so if we take certain intervals and find the value of f of x there, then using those intervals, we can say that the average of the function is the sum. Again, you need to take the sum of all these values and then basically divide them by the length, right? So the sum uh, of all the values of the function x plus the width times the number we're taking. So if you imagine this to be the first interval, this is the second interval, this is the third interval, this is the fourth one, and so on. We can, and if we give that a number, which would be, and if we give that a letter, uh, let's say m. Okay, so the number of the interval number, let's call it, is equal to m. So if I wanted to find the x value of the fourth interval, I'd have to multiply m by the, the difference of each interval, which would be n. So I'd have to multiply m and n. I'm going to write that in green and in blue again. So for the mth interval, we would need to add this x value that starts at 0, let's say, to by that value. So let this be x at 0, which is our starting point, and then we keep adding the multiples of the interval that we've chosen, and then we divide this by the number of intervals. So the number of intervals should be a over n, correct? Because a is the length, technically a minus 0, but since we're starting at 0, the length of the entire interval that we want the average value of, divided by n, which is the interval length, which should give us the number of intervals. So what we're doing is and if we take a value I, so it should start from I is equal to 0 and go on till the a over nth term, because there are a over n intervals between 0 and a. And so we get something like this, which should be the average value of the function. If we say that, let's say n is equal to 0.1, and then we would have a upon 0.1 intervals between 0 and a, and where m is the interval number. So what we're doing here is we're adding each value of the function at these points, and since they're all equal, we do not have to weigh them, so multiply them by different constants, and we're dividing them by the number of intervals that we take, and that should be the average value, and that should be a good approximate of the average value. However, there are points where technically f of x would be this right here when it actually should be this. But if we decrease the interval length, let's say I make it half of n, then if you notice that it's going to get untidy if I actually draw all of them, and those gaps start getting filled more, and well, we want an infinite number of points, and so a good way to do that is if we could make that n tend to 0, we would have an infinitely small interval, and so an infinite number of intervals before 0 and a, between 0 and a, and that should give us a very good approximate of what the average value should be. So if I change this function that I've written here to limit n as it tends to 0, then a over n should tend to infinity. So we can write this down as m is equal to 0, so as it goes to infinity, f of x, and since n tends to 0 over here, it would just be f of x, and it would be upon a times n, as n is going to infinity still. Just a better way of writing it right now. And if you remember from our previous calculus lesson, if something tends to 0, since it's an interval, we're saying that it's a difference between the two values, right? This n is an interval. It's a difference between these two x values. And when that becomes really small, we can always just replace it by a delta or a d uh, alphabet. And here it's a small, infinitesimally small change in x, and so we can write it as dx instead. And a better way of writing this sigma would be just to show that it's not really taking the sum anymore, because the sum has to be of discrete finite elements usually. Uh, it's an integral now. So we say that it's an elongated s for sum of f of x times that dx, since n is an infinitesimally small change, upon a. But that's just another way of writing this right here. So, and what this means is what I'm going to explain to you soon. And this is what we call an integral. This infinite sum of all the values times a really small change. And since this has just gone up here and this is the length of the interval, this whole thing should actually just be the average value of the function. And since we're doing this integration between 0 to a, we'll just write down that this is from 0 to a. And if you notice, the reason why it's called integration is because we're combining all of these tiny, tiny values, we're integrating them to give us something that's useful. And through this, we can get a very good approximate of what the average value of the function is. But now, what does this signify is something that I will explain to you. So, if you noticed on in over here, if we made these lines and we did calculate the average, let's say the average was a, then that average is equal to the and here again we're assuming that they're all equally spaced, right? So they're all 1, 1, 2, 3, 4, right? And so if the average value a is the sum of all these, would technically be the sum of all these values times the sum constant, which in this case is 1. But let's say that difference was n, and each of those values was, let's say, m1, m2, m3, each of these values over here, and the difference was n. So we'd get something like m1 times n plus m2 times n plus m3 times m, and so on. I'm just going to stop at 3, but it can go on for longer, divided by the number of them, which is 3 times n, and divided by this entire interval, which is from 0 to 4, which would be 4, but in this case I'm just going to give it another variable, let's say L, right? So L is the number of terms, right? And if you notice, if I multiply AL on this side, that would be equal to m1 times n plus m2 times n plus m3 times n, and so on if there are more values. And if you look at this over here, that would actually be the value over here times its width, and then this length times its width again, and this length times its width again. So if you notice that this number would actually give you the area of this entire graph. And similarly, if we look at this again, then multiplying on this, then getting the average value of f and multiplying that by a being the interval, being the size of the interval, we should get the area under the curve between that interval that we have decided to integrate over, because we're multiplying the height over here in each case by this n, which is the interval, it's the size of the interval. And if we multiply the height in each case by the size, we start calculating the area. And then by limiting that interval to 0, we technically just calculate the entire area of this curve, which is pretty fascinating. And the reason that I didn't show it to you as calculating the area first, but rather as the average value of a function, is because it's a much better way to understand what integrals really are and how they relate to derivatives. So this is what an integral is. What an integral actually gives you is the area under a curve between these two values of x. And if you notice, it's basically the height multiple times, that's f of x, multiplied by the small infinitesimal changes in x, giving you an infinite amount of length times heights, and that is basically the area of each of these infinitesimally small columns, which gives you the area of the entire function. Hence, the area of a curve from a to b is the integral from a to b of f of x dx, as defined before. If this is the integral and that is the function f of x, then this would be f of b minus f of a.